Hello everybody and welcome to our second lecture on chemistry. So remember that this is biology, but when talking about biology, we have to talk about certain chemical aspects. So if you guys don't like biology, I'm pretty sure there's a good chance that you're not gonna dig chemistry either. But this is just one little section that we're going to be going through, and then we're going to be moving on. So unfortunately, a lot of the concepts that we're going to be talking about in the future, though, have to do with this general chemistry stuff. So even though this is biology, we are going to have to get into a little bit of the chemistry of it. So that's what we're going to do right now. So bear with me. We're going to get through this. Trust me, it's going to be okay. All right. So let's start talking about chemistry. So chemistry is the study of matter. And matter is essentially anything in the universe, just anything that takes up space and has some kind of weight to it. So even if we're talking about these little atoms that are like floating in the air right now, which you can't even see, they do take up space and they do have some kind of weight to them. In fact, pretty much everything does. Even when we talk about electrons and stuff like that, we're still going to actually have a calculable weight to them. So that is the study of matter, right? Chemistry is just the study of matter, and matter is pretty much just anything, right? This is matter, floating in the air, that's all matter. Right? And it all matters. First terrible dad joke of the day. So, remember that we are studying matter when we are studying chemistry. Now, matter, hopefully you guys kind of remember this from like elementary school, comes in three different states. Right? We have the solid, the liquid, and the gas. Those are our three physical states of matter. So if you think about it, like water is a unique one because water can actually be found in all three states naturally on our planet. In fact, water is one of the only, molecules that can actually do that, which is pretty cool. And in fact, our second half of the lecture today is going to be all about water. So we're going to learn a lot about water today. All right, so first off, we have to start talking about elements. Now, when you're talking about chemistry, you can't talk about chemistry without talking about an element. So an element is a simple substance that cannot be broken down into any other substance. So if you're talking about carbon, or oxygen, or nitrogen, or phosphate, or boron, all of those are naturally occurring elements on our planet that cannot be broken down into anything else. You can't take carbon and break it down into nitrogen and hydrogen, because it's not made of nitrogen and hydrogen, it's only made of carbon. Okay, so any element is something that cannot be broken down into something else. So there's now 92 naturally occurring elements on our planet. We have been able to kind of like synthesize some more or create some more, which is kind of cool. But am I going to ask you guys to memorize all of these? No. Am I going to ask you to be able to identify maybe a couple of the most common ones that we talk about? Yeah, but that shouldn't shock you guys because, we're going to talk about them again and again and again and again. So let's go into a little bit about the periodic table. Now, there's a lot going on with the periodic table. All of these different colors that you can see right here, these are different types of elements. So we have our alkalines, we have our alkaline earth metals, we have our transitional metals, we have our, noble gases. We have all sorts of different elements and types of elements, and therefore they're arranged in the periodic table as such. Now, luckily for you guys, this is not a chemistry class, and therefore we're not going to be going into super crazy detail about this, but I do want you to understand this and kind of know what's going on. So, where to begin with the periodic table? This is a little video on the periodic table. I'm not going to show it to you guys here in this video, but I would highly recommend that you guys watch it. It tells you about periodic trends and stuff like that. Kind of explains like why everything's built the way that it is. Now, let's just go ahead. Let's just move on before we actually get into the nitty-gritty of these elements. All right. So when we have an element, remember it is a single element, a single substance that cannot be broken down into any other substance. Carbon is carbon. Oxygen is oxygen. Oxygen is not made out of anything else. It's just oxygen. But what you can do is you can take some of those different elements and you can stick them together to form what's called a compound. Okay, so this compound is several different elements together. So you can say a compound, you can also call it a molecule. Anyway, we're building up on these smaller little individual elements and we're building it up into something larger. So say I take two hydrogens and an oxygen and I stick them together. Now I have H2O. Now I have the molecule of water or the compound that is water. Okay, it's made of hydrogen and oxygen. Hydrogen and oxygen can't be broken down into anything else. But when you put a bunch of elements together, then you're actually forming a molecule or a compound, and that can actually be broken down, right? That water can be broken down into 2 different hydrogens and 1 oxygen. Okay, so that's the difference between a compound and an element. So here we have some classic examples. So the one I just talked about, H2O. We also have this one right here, which is sodium chloride. The Na is sodium, the Cl is chlorine. You put them together, they're sodium chloride, right? That is table salt. And that's one that we're going to see a lot in this class. So very common, some of these compounds, water and table salt. Now, we have elements that are necessary for life. So we are living organisms, which we're going to learn about later on in this semester. Actually, we already learned about living organisms, right? What does it mean to be alive? That was chapter 1. That was introductory to biology. What does it mean to be alive? We have to have these several different things to be alive. So since we are living organisms, we require certain elements to survive. Now, there's about 25 of them that we absolutely need to live. But am I going to ask you to know all 25? Absolutely not. Am I going to ask you to maybe know which one is the most abundant in our body? Yeah, yes I am. So let's go on to that. So there's about 4 that are really, really, really crucial to us. These 4 you will need to know, and especially which one is in the number 1. So you can see right here, this big piece of red part right here of this man, this is oxygen. So oxygen takes up about 65% of what makes us us. Now, this isn't just you're a big balloon of oxygen and you're going to float away. No, oxygen is combined with other things. H2O, there's oxygen in that. That's flown all over your body. Things like glucose, C6H12O6, that is all over your body. That's a bunch of oxygen. So no, you're not a big bag of air. Some people might be, right? No, we're actually just made of again, these compounds with oxygen in them. So that's what I mean by 65% of oxygen, makes up the human body. Now, when we continue on down here, you can see that carbon is another big one, right? This gray part right here is carbon. So we are carbon-based life forms. That's something that we kind of learned about. So we have a basis, actually, that's next semester, or next chapter. So we are carbon-based life forms on this planet. So a big part of us is made out of carbon. The next up, we have hydrogen and nitrogen right here. So again, the big one is oxygen, followed by hydrogen, nitrogen, and oxygen, carbon, hydrogen, and nitrogen. There it is. I'm rusty with my lectures, if you can't tell. All right, so these all the way down here, these are the little yellow ones. These are known as trace elements, right? These trace elements are found in very, very small amounts. So you can see all these trace elements that are right here, things like boron and chromium and cobalt and iron and stuff like that. So these are still necessary to live. In fact, especially things like iron. If you have an iron deficiency, you actually have to take iron pills because your body needs iron. And you're like, wait, my body needs metal? Yes, it does. Right? Fun fact. But they're trace elements because they're found in less than 0.01%. So just a little bit, but we still need them and they're still crucial for life. And then these ones right here, these ones are all anywhere between 0.1 and about 2% of our body. So again, big, variety of these different elements that we need to survive, but we do need absolutely all of them, even if it's just in trace amounts. We're actually going to see what happens if you don't have things like iron. So, if you have an iodine deficiency or fluorine deficiency, some nasty little things can happen. So these trace elements, again, are just found in tiny little bits, in tiny little amounts, but they're still totally necessary to live. So if you do have this iodine deficiency, what you can get is a big old goiter, and that's what we can see right here. This poor lady has this swelling right here in the throat. It's just this giant fluid-filled ball. And can you imagine putting something under your skin and stretching out your skin that much? No, that would really, really hurt, and that's what these goiters do. They're actually really painful. So that's just caused by a little tiny bit of iodine getting out of whack in your body. I know. It is so incredible on how we don't just perish every single day. Because if 0.01% of our body's out of whack, we get a goiter, right? And if 0.2%, or heaven forbid 2%, we just die. It's crazy how fragile we really are. So yeah, tiny little bit of iodine deficiency, you get a goiter. What else? Things like fluorine, right? A lack of fluorine in your diet will actually cause really nasty teeth decay, which can cause all sorts of different health problems. Oh my God. People die from tooth issues and infections and stuff because they get up in there, and it's all sorts of nasty and bad, which is why most cities, especially here in America, we actually add fluorine to our water. Did you know that you're drinking a chemical What? I'm drinking a chemical? Yeah, that word chemical is not always a bad thing. Guess what? Water's a chemical. Table salt's a chemical. They're all technically chemicals, right? Because they went through a chemical reaction. It doesn't mean that they're bad. So this is something that I'm going to teach you guys throughout the semester. Remember when we learned the word like theory or versus theory, right? It's a theory, not a theory. I'm not guessing here, right? So it does, just like the word chemical doesn't necessarily mean it's a bad thing, right? It's just that negative connotation that people put on the word chemical. So you guys are going to know better. That's right, because you're in my class. All right, so now let's get on to what actually makes up an element. And you're like, well, elements aren't made of anything else. You know, carbon is carbon. Yes and no, because it's still a carbon atom. And hopefully you guys remember what an atom is. An atom is the smallest unit of matter, right? It's the smallest unit that can exist on the planet. Everything is made up of atoms. My shirt, my hair, my skin, the air, everything is made up of atoms. Now, inside an atom is going to be 3 different parts. We have a proton, we have a neutron, and we have an electron. Or we have, protons, neutrons, and electrons. Now, remember that a proton has a positive charge. A neutron has a neutral charge, not negative. People love to go, P positive, right? And negative, no, and is neutral, hence neutron. And electron, which is the negative. So we have the protons are the positives, the neutrons are the neutrals, and the electrons are the negative ones. So these atoms essentially get together to form these compounds, right? So if you take 2 atoms and you stick them together, now you actually have that compound. You take 2 hydrogen atoms and an oxygen atom and you stick them together, and now we have water. Okay, so this is building those compounds that we already talked about, or those molecules. Like you have a molecule of water, which are slightly different than compounds, but again, this isn't a chemistry class, so we're just going to simplify and make things a little bit easier for you guys to understand. So let's take a look at what an atom actually looks like. Hopefully this is kind of familiar to you guys if you watch The Simpsons, right? The isotopes symbol, that's an atom, right? And that's because, this is a study of chemistry and they're, a nuclear reaction. Or nuclear reactive team? I don't know what I'm trying to say here. I'm getting off on The Simpsons. This is not what we're talking about. All right, so here we have the protons, we have the neutrons, and we have the electrons, right? All of these make up an atom. So what we have right here, actually let's do this one first right here. This one's a little bit easier to understand. These two are the same pictures, they're just kind of represented slightly different. This is the cloud model, this is the ring model, or the orbital model. I usually like to go with the orbital model. It seems like a little easier to understand. So on the inside, we have a nucleus, okay? Inside the nucleus, you can, it's kind of like, just like a cell, like the nucleus is kind of like the center, like the really important part. So you want to keep that protected. So inside your nucleus, you're going to have your protons and your neutrons. Okay, so those protons and neutrons are in the nucleus. They never go anywhere. They're stuck in the nucleus. They're safe in the nucleus. They're tightly packed in that nucleus, and they're not going anywhere. So like I said, protons and neutrons are located inside this nucleus right here. Now, floating around the outside, and you can see in the orbital model, we have 2 protons, 2 neutrons, and floating here and here, we have 2 electrons. Now, the electrons are going to be the whole reason that any kind of chemical reaction exists, right? So in a chemical reaction, the electrons are the ones that are reacting, not the protons, not the neutrons, not the nucleus, right? Those are tightly packed. It's going to be the electrons. And that's because the electrons are actually floating around the nucleus. And that's why you see this one represented as a cloud, because they buzz around so fast, right? It's like a blur. It's like a cloud, essentially is a cloud, which is why they draw it like that, okay? So this is the orbital model. It makes it a little bit easier. It's like you just took a picture real quick and it's like frozen. So you can see 2 electrons here floating around that nucleus. So, again, protons are positive, neutrons are neutral, and electrons are negative. Now, this is really important when we talk, coming up in the lecture, when we learn about certain things, when it comes to an atom, the number of neutrons can vary. Right? The number of neutrons can vary. Sometimes you lose a neutron, sometimes you get a neutron. They're just naturally kind of occurring like that in nature. And those are called isotopes, is when the neutron varies. Now, the electrons in an atom can also vary. As they're floating around and they're whirling around, sometimes, poo, they go. Or, poo, you get one. Okay, so those electrons can be transferred. And those are called ions. If you've lost or gained an electron, that's called an ion. So, just to and we're going to learn about all this coming up in the slides, but I just want to let you guys know. The number of electrons can vary. The number of neutrons can vary. The number of protons can never vary. The number of protons is what makes your element your element. If you're talking about you have 6 protons, you're carbon. That's it. You can't be anything else. Because if you had 5, you'd be nitrogen. And if you had 6, you'd be, if you had 7, you'd be oxygen. I think I did that backwards. Anyway, I'm just, again, I don't have the periodic table in front of me, and I'm obviously don't remember the exact number of these, nor should you, right? I'm not going to ask you. I'm going to show you the periodic table, or I'm going to give you the number of protons or something, so you'll never have to guess, or like, I don't know. But you do need to know the number of protons is what makes an element, right? The number of protons cannot vary. Hydrogen only has, well, technically 1, right? Helium has 2. Lithium has 3. Beryllium has 4. Right? That is what makes that element that element. If it did vary, it would be a whole different element, and we can't do that. Okay, so again, the number of electrons can vary. You know, carbon, let's see. Fluorine can gain an extra electron. It's still just fluorine. Chlorine can lose a couple of electrons, and it's still just chlorine, right? But the number of protons, again, is what makes that element the element. Okay, I'm getting there. All right. Now, that number that I was just talking about, the number of protons, the one that makes that element that specific element, is called the atomic number. Okay, so the atomic number is how many protons you have. Okay, so if I'm lithium, I have 3 protons. That's it. Can't ever change. Yes, I can vary in the number of electrons I have. Yes, I can vary in the number of neutrons that I have, but I can't vary in the number of protons. That is what makes the element the element. That is the atomic number. Now, the mass number essentially is the number of protons and neutrons located in your nucleus. So inside your nucleus, say if I'm lithium again, I have 3 protons. That usually means that I have 3 neutrons. Not always, but usually the number of protons and neutrons and electrons are usually the same because that's a balanced element. That means that element has no charge. If it was positive, that means that it has more protons than electrons. Remember, the neutrons don't have a charge, so that can't affect your charge, right? So think you have 3 protons, 3 positives, and you have 3 electrons, 3 negatives, right? They cancel out. So you're essentially at 0. So you have no charge. So lithium would just be lithium, right? Just an element. So we would add up the 3 protons plus the 3 neutrons to give us our mass number. Okay, so that's kind of, and you can think of mass almost as weight. It's not exactly weight, but it's almost like weight. And again, this is not a chemistry class, so we're just going to kind of like how much it weighs, kind of thing. Mass number. What is the mass number? And then finally, the atomic mass, here's the one that's kind of confusing. It's actually the atomic number and the mass number kind of combined, which is really weird. So it's like an average of the different types of isotopes that you have. So remember that an isotope is just varying in the number of neutrons. So say I'm lithium. I have 3 protons. That makes me lithium. I have 3 electrons because I'm not charged. I'm not an ion. I'm just lithium. I'm just an element. Okay, but say now, maybe instead of 3 neutrons, maybe I have 4 neutrons. Just naturally occurring in nature, we have 4 neutrons. So you basically take the average of the lithium 3 with 3 neutrons and then lithium 4 with 4 neutrons. You average that out, and that's what the atomic mass is. Now, I will never have you guys calculate this. So you're like, wait, what? I don't understand. That's totally fine. As long as you understand the definitions, because remember, this is just conceptual. We're not going into actual calculating of any of this, then you'll be fine. So don't stress on, I don't know how to calculate. Don't worry about it. If you do want to learn how to calculate it, here's how. So let's go with an example of carbon. So again, we're talking about carbon, the element, which has 6 protons. Never going to change. Look, protons, protons, protons. Always 6. Okay? Because it's carbon. If I was 5, I'd be something else. If I was 7, I'd be something else. Fluorine. So carbon is still just carbon with 6 protons. Now remember, I told you that the number of neutrons can change and the number of electrons can change. In this case, we're talking about the number of neutrons changing. Okay, so the number of electrons is going to stay the same, right? But we're talking about, in this case, isotopes. And an isotope varies in the number of neutrons. Still carbon, still just carbon. But in this case, we have a carbon 6 because it has 6 neutrons. Carbon 12. Because we add the protons plus the neutrons, which gives us the mass number of 12. Okay, so that's how we get the mass number if you want to calculate. Number of protons plus number of neutrons gives us 12. So in this case, they would call it a carbon-12 because it has 12 as the mass number. Now, if we look over here, we actually have carbon-13, and that's because right here, the number of neutrons now goes up to 7. Remember, the number of neutrons can change without changing the element itself. So now we have 7 neutrons plus the 6 original protons gives us carbon-13, right? Because the mass number is now 13. Alternatively, if we go all the way over here, we now have carbon-14, and that's because it has 8 neutrons plus the 6 original protons gives us a mass number of 14, hence they call it carbon-14. So, again, they're all just carbon. They just vary in the number of neutrons present. Don't stress too much about this. Again, it would be simple math like this if I ever gave you anything. Like, what's 6 plus 8? I'm pretty sure you guys can do all that in your head. All right, so this is isotopes. Again, the varying number of neutrons in an element. All right, so remember that the atomic mass, well, actually, it's, all right, so the atomic mass is kind of, it's the really confusing one. The mass number is pretty straightforward. The atomic number is super straightforward. The atomic mass is kind of a little bit different. It's very, very close to the mass number because you're just taking an average of those neutrons. So again, we had the 6 and the 7 and the 8 when it came to the carbon, so the average would be 7. Okay, so the atomic mass would be 13, whereas the mass number would be 12. So very, very close, just slightly different because you're taking the average of the isotopes. And again, this is like the only time we ever talk about isotopes, so don't worry. We're going to talk about ions more, but we're only talking about isotopes just a little bit here. All right, for whatever reason, this is another version of the periodic table. We're going to just keep scorping on here. Now, why do we care about isotopes? Well, isotopes are actually really handy. They're really useful in lots of different things. In medicine, in like medical research and stuff like that, using x-rays, we can actually look at all of these different things. So in fact, we can actually do scans of our body and look at the isotopes found inside some of our organs and detect early organ failure. That's pretty cool because you're actually looking at the isotope and what's called the decay rate of the isotope. And you can look at it and be like, whoa, it's supposed to be here, but the decay is all the way over here. There must be something wrong. So we can determine some of these things really, really far in advance, like some cancers, some Alzheimer's. So this is why early testing is so important, because if you catch these isotopes in the early stages of decay, you now know that there's a problem. And then you can actually start treating said problem way before it actually starts to manifest into like severe, issues. So these radioactive isotope decay, or the decay rate, is kind of what we can look at. So we can look at this little radioactivity and we can determine, where we are in certain medical stages. Now, this isn't just true of medical stages, it's also true of things like fossils and carbon dating. I'm sure you guys have heard of like carbon dating, like, oh, we know that is, 1.2 billion years old. How do you know it's 1.2 billion years old? You weren't there. You look at the rate of the decay. And again, we know the rate of the decay, and so you can say, oh, if it is, this far into the rate of decay, then it must have started here. It must be like, 300 million years old. I think that's fascinating. So we can look at some of these different types of isotopes, and we can look at their essential decay and determine how old it is. I don't know. That's super fascinating to me. So again, isotopes, really, really important. Just slightly varying in the number of neutrons. You look at the decay rate and you can determine things like Alzheimer's and early cancers, as well as carbon dating and dating these fossils and remains and rocks and stuff that have been around forever. So super cool stuff. All right, so let's talk about electrons again, because we talked about how we can vary in the number of neutrons. That's our isotopes. Now we're going to be talking about varying in the certain number of electrons, and these are known as ions. Now remember, I told you guys that electrons are the ones that are responsible for the chemical reactions. So any kind of reaction that's happening, it's always the electrons. In fact, it's always the electrons on the outermost shell. So remember, we had the neutron on the nucleus on the inside, and then we had the electrons on the outside. Well, what happens at a certain point is those shells get full. And once they're full of electrons, they're happy. In fact, they're stable. They're like, I'm full, I'm super happy, I'm not going anywhere. Okay, they're all trying to get to this full electron shell. And if they're not full, then they're going to be reactive. Say they only need one more electron. They're all trying to get to a certain number. That number is usually, in our class, it's either going to be 2 if you're the first shell, it's going to be 8 if you're the second shell. We're going to learn about why that is in just a second, don't worry. So let's look at this and determine the reactivity of certain stuff. So remember, we're only looking at the outermost shell, because the inner shell, you'll only get, we have the nucleus. You have your first shell. Once your first shell is full, then it's stable, it's not going to go anywhere. Then you add a second shell, and a third shell, and a fourth shell. Every time one gets full, it's done. That's it. It's full. It's not going to happen. Nothing's going to happen with it now. It's full. It's like, essentially, it's done working. Okay, so then you add another one, and then you add electrons to that shell until it's full. So, if the outside outermost shell is not full, then the element would be considered reactive. And certain ones are always reactive because they're not full, and therefore they want to react. So let's take a look at some of these real quick. Okay, so again, we have the nucleus on the inside. That is not reacting at all. Not reacting. Oh, the protons and the neutrons, not reacting. Protons make up the element. Neutrons, handy for isotopes, but the electrons are the reason that the reaction's actually continuing. So we have our nucleus on the inside, we have the electrons on the outside. Now, what you can see right here is the yellow represents an actual electron, and the little white part right here is an empty space for an electron. So if I'm hydrogen right here, hydrogen desperately wants 2. Okay, so 2, again, would fill up the first shell. The first shell of every element can only hold 2. So if we look here at carbon, you can see the very first innermost shell has 2. It's full, right? That's good. Now it builds the second shell. So the first shell always needs 2. The second shell needs 8. Okay? This is known as the Octet Rule. Everybody's trying to get to 8. So to fill up your outermost shell, in this case, you would need 8 electrons. So in this case, we have carbon with 1, 2, 3, 4 electrons, which means carbon needs 4 more electrons to have its outermost shell full, which is why carbon is really reactive. Because carbon's like, I need electrons. Who's got electrons for me? Well, hydrogen out here has 1 electron and needs 1 electron. So hydrogen and carbon usually actually pair up. In fact, you'll get 1, 2, 3, 4 hydrogens around a carbon molecule, and you'll form CH4, which is methane. If you don't know what methane is, it's that really stinky stuff that comes out of your backsides or the backsides of cows. Yeah, it's like farts, essentially. But it's a really stable molecule because it's happy. And we're going to talk about why that is in a second. If I had a board, I would draw this for you guys. Maybe I can get a piece of paper and draw this for you guys. We're going to figure it out. All right. So let's go back to hydrogen real quick. So hydrogen has 1, but it needs 2. So hydrogen is also really reactive, just like carbon. It's always like, oh man, who's got 1 extra electron for me? I just need 1 more. Okay, so it's trying to react. Same thing with nitrogen and oxygen. You can see right here, they both have missing electrons in their outermost shell, which means they're looking to fill their electrons up. Okay, so what they do is they'll actually come together. So let's go back to methane real quick. We have our carbon and we have some hydrogens floating around. Those hydrogens are going to naturally be attracted to this electron here. In fact, each of these electrons on the outermost shell, because they're trying to share their electrons to make them both happy. So essentially what they do is hydrogen comes over and almost like holds the hand of carbon and goes, hey, we're going to form a bond. This bond that we formed right here between the 2 elements, my elbows are the elements, this right here is the bond, is a sharing of electron. So say hydrogen's over here and carbon's over here. Okay, hydrogen needs 2 electrons. It already has 1. Now carbon has some that it can share, and so carbon and hydrogen get together and they form a bond. Now, technically, hydrogen has 2 electrons. Hydrogen is now happy. Hydrogen is a full shell. It's like, I'm stable. I'm good. Okay? Carbon is still looking for some more electrons, so it picks up 3 more of those hydrogens. So now carbon is forming a bond here and here and here and here with 4 hydrogen molecules. So carbon now technically has the 8. It's happy. Hydrogen has the 2. It's happy. Everybody's happy. So the sharing of electron that we're doing actually makes everybody more stable. Okay, and we're going to keep talking about this, and I'm going to show you guys more examples of this. But this is kind of how you can kind of predict who's going to be reactive. So you look at the outermost shell. Can you see, oh yeah, he's missing some electrons. Yep, so is he. Both of them would probably be reactive. This is how we build things like water molecules and sugar molecules and all these larger molecules, because they're getting together to share electrons, because they're unhappy when they don't have the right number of electrons. And they're just basically like bouncing around going, who's got an electron? You do, cool, let's hold hands, right? So then they share the electrons and everybody's happy. Now, actually, I'm going to go back real quick. I'm going to show you this one. It's a little bit easier to understand. Now, how do we tell who is going to be reactive and who's not going to be reactive? Well, it's kind of actually easier than it looks. So it is set up in very organized way. So what we see right here is that these are columns right here. Okay, don't worry about everything else in the middle. These are known as transitional metals. They kind of work a little weird. So we're not going to worry about those in our class because it's not a chemistry class. We're going to be focusing on these first 2 columns right here, and then these other 6 columns right here. So if we look at the top, this is 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. This is the easiest way to tell how many electrons are in your outermost shell. Don't worry about the total number of electrons. This is something that we would have done in class, but obviously we're not in class, so we're going to skip it for this semester. So what we're going to do is we're going to look at that column number. So in this case, in our outermost shell, if we were in row 1A, that means in our outermost shell, we have 1 single electron floating around. Okay? Remember, in our shells, we're always trying to get to 8, except the first shell. The very first shell is just trying to get to 2. And I can actually explain why that is. So if we look on the very first row, right here, notice how many elements there are. There are 2. That's the first shell. The first shell can only hold 2. 1, 2, that's how you remember it. Boom. So you can act like this right here is the first shell. All the way across, there's only 2. Okay, we go to the next row. 1, 2, 3, 4, 5, 6, 7, 8. That's where I got that number 8 from. It's right here in the periodic table. So it's actually pretty easy to understand if you just look at the periodic table. And of course I will give this to you if I'm actually going to put a test question like this on the test. So we had row 1, we had 2 elements. We go to the next row, we have 8. We go to the next row, we have 8. And that's where our class stops, because don't worry about all this stuff in here. This is not chemistry. I could teach it to you, but this is not a chemistry class. All right, so we're always trying to get to 8. And this row right here, this column right here, is known as the noble gases. The noble gases are so noble because their shells are full. They're like bragging. They're like, our shells are all full, hence we're noble. We don't need any electrons. We don't need anybody else's help. These guys are not reactive. Helium is not reactive. Neon, Krypton. Yeah, there is an element called Krypton, guys. These are non-reactive because they're stable. Their outermost shell is full, and therefore, they're not going to react with anybody. Okay, so any of the noble gases, anything right here, is full. It already has 8. Okay? Now, if you don't have 8, if your outermost shell is missing any electrons, right? Be it missing 7, missing 1, those are known as valence electrons. Okay, so valence electrons are the ones that are going to be reacting. Those are the ones in the outermost shell. We're not talking the total number of electrons that you have. We're just talking about the valence electrons. So let's give an example. Let's see, I'm boron. Okay, how many valence electrons would I have? Well, I would have, what's boron? I would have 5 total electrons. But the first 2 are going to be locked up in that first shell. Okay, so really, the way you count how many valence electrons you have is by the row. I'm in row 3A, which means I have 3 valence electrons. Okay, let's just go to someone else. Let's say I have iodine way down here. I'm in column 7A. That means I have 7 valence electrons. It's literally that easy. Okay, it's not that hard. Again, if we're going to go over here, let's talk about magnesium. I'm in column 2A. I have 2 valence electrons. That means I'm trying to get to 8. I only have 2. Okay? Finding 6 electrons somewhere is probably way harder than it's worth. But getting rid of 2 electrons is kind of easy. Okay? So again, say I'm magnesium over here. I've got 2 valence electrons in my outermost shell. I'm trying to get to 8. The chances of me picking up 6 are probably pretty low. So instead, I'm just going to ditch 2 of mine. Okay? Because someone like oxygen over here has 6 valence electrons. It only needs 2. So in this case, oxygen's like, dude, I'll take your 2, and magnesium's like, great, I'll give you my 2, therefore forming a bond called magnesium oxide. Okay, so in this case, and this is known as ionic bonding. So when we were talking about the sharing of electrons, this is known as a covalent bond. Sharing of electrons, covalent bond. And I can tell you, covalent bonds, the sharing of electrons, are the strongest of all the bonds. Ionic bonds are like a temporary loan system. Magnesium is giving away its electrons, but only temporary. It's still magnesium's electrons. It's not going to give them up for good. It's like, here, you can borrow these. Just take them for a little while. And oxygen is like, great, I'll take those for a little while. So an ionic bond is a transfer of electrons. You're transferring your electrons to another element temporarily. Okay? Covalent bond, sharing of electron. Ionic bond, transfer or receiving of an electron. Okay, so in this case, magnesium would be transferring 2 of its electrons, and oxygen would be receiving 2 electrons. So they still form that bond, but it's known as an ionic bond. Okay? So that's kind of how you can tell with the periodic table, like whether they're going to be reactive or not. So I could ask you a question could lithium over here pair up with fluorine? Think about it. Could it? Would lithium react with fluorine? Well, let's see. Lithium has 1 valence electron in its outermost shell. Okay. Fluorine has 7. So fluorine needs 1, and lithium has 1. So yes, they could absolutely react. In fact, you'd form lithium fluoride. Okay, now what about, say, sodium and nitrogen? Sodium and nitrogen, can they form together? Well, let's see. We have sodium that has 1 valence electron in its outermost shell, and we have nitrogen, which has 5 valence electrons. So 1 plus 5 equals 6. That's not 8. Right? So in this case, you have to hit your 8. If you're not going to hit your 8, you're not going to be reactive. So in this case, sodium and nitrogen would never react together. At least not without adding some other element to it to make up that total 8. So hopefully that kind of explains it a little bit better, kind of what's going on here. Again, usually this is something that we do in class, so if we don't really have the time to do the in-class stuff, again, don't stress too much about this. This is big picture kind of stuff right here. So just, how many valence electrons does it have? Oops. Look at the column name. 1, 2, 3, 4, 5, 6, 7, 8. Right? These are the noble gases. Everybody's trying to be noble. Everyone's trying to get to that 8. Of course, unless you're in the first row and then you're just trying to get to 2. So hydrogen is really just trying to get to 2. And hydrogen's the only one who wants to get to 2. Everybody else is like, we're trying to get to 8. Okay. Let's go back to where we were. All right. So again, valence electrons, this is a simplified version of what we were just looking at, right? This is column 1, column 2, column 3, 4, 5, 6, 7, and 8. Just getting to that octet rule. So again, it's the valence electrons that are doing the reactions. The electrons in the outermost shell. Not all the electrons that you have. You could have 117 electrons and still have, actually, let's look that up. Let's see if we have 100 and, just kidding. It stops at 103. Oh no, it's at 117 right here. So we are, I've never even, uniseptus. Oh, not an element I'm familiar with. But you have 117 total electrons. You still only have 7 valence electrons. So there's still only 7 of your electrons that are actually reacting. The rest of them are stable. Okay. Okay. So this is exactly what we were talking about with those bonds. So in this case, we have an oxygen with its inner shell full. Inner shell is not reacting. And its outer shell with 1, 2, 3, 4, 5, 6 electrons. So oxygen's like, I need 2 more. How do I get 2 more? Well, hydrogen has 1, and another hydrogen molecule also has another 1. So now if we get our 6 from our oxygen, 1 from each of the hydrogens, now oxygen, technically because they're sharing, has 8. So now oxygen is happy. Oxygen is happy. Each of the hydrogens are happy because each of them have 2, right? 1, 2, hydrogen's happy. 1, 2, hydrogen's happy. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's happy. The water molecule is now stable. And that is actually really, really true of all water molecules. Water is one of the most stable organisms, one of the most stable compounds out there because it is balanced, right? And it's not ionic. It's not like, here's my temporary electron, but I'm totally going to take that back later. Ionic bonds are actually pretty easy to break. Covalent bonds, because they're sharing and every molecule's happy, every molecule is going to fight you and be like, I'm not breaking. I'm happy. We're all happy. We're not going to break apart. It takes a lot of energy to break up these bonds. Hence the covalent bonds, which would be the sharing of the electrons inside the water molecules, making it a very, very stable molecule. And again, these are just known as chemical bonds. All right. So remember, ionic bonds are going to be donating or receiving of electrons. And that's what we can see right here. We have sodium, right? All of the inner shells are full. Don't worry about that one. But sodium has this one lonely electron on the outside. Remember, because it is one valence electron. And it's really sad. It's like, I am not even close to having 8. Chlorine has 7. Chlorine's like, well, I'm really close to having 8. So why don't you just give me your 1 electron? You'll go down. You'll lose that outermost shell because there's no electrons there, which means your outermost shell will be full. You'll be happy. My outermost shell will be full. I'll be happy. We form sodium chloride, table salts. So we form that sodium chloride, that ionic bond, right? This sodium gave chlorine its extra electron. So now its outer shell is full. Chlorine's outer shell is full. It's happy. This is known as an ionic bond. However, this is kind of like a temporary thing because sodium has lost one of the electrons it's supposed to have. Okay, so now instead of having the same number of protons and neutrons, it has protons and electrons. It has less electrons and the same number of protons, so now it has a positive charge, right? Because remember, it had no charge when the number of protons was the same as the number of electrons. But now we've lost an electron. So now we're slightly positive, and that's what you can see right here. This little plus symbol means that sodium is slightly positive. This is called a sodium ion. Right? If it's just sodium, it's called a sodium element, right? It's just sodium, or a sodium atom, right? It's just a single bit of sodium. But as soon as it becomes charged, either with a positive or a negative, right, now it's considered an ion. Okay, so this would be a sodium ion. Same thing with chlorine. So chlorine had the same number of protons as electrons, but now it gained an extra electron. So now chlorine is slightly negative, right? Because it is more negative than positives. Okay, so chlorine becomes slightly negative, right? So the Na plus is a sodium ion. The Cl minus is a chlorine ion. Okay, so that's what it means to be an ion. It has to have some kind of charge. If it's neutral, then it's just an atom or an element, right? It's not an ion. And ions are charged, meaning with the positive or the negative, just like your batteries. All right, so let's look at this example. We have fluorine and we have potassium. Would fluorine and potassium get together? Would they react, should I say? Well, let's look. Fluorine has 1, 2, 3, 4, 5, 6, 7 in its outermost shell. So fluorine's not quite to that octet rule, not quite to the rule of 8 yet. And potassium has, just the 1. So yes, in fact, this case, potassium and fluorine would absolutely get together and they would have an ionic bond. Okay, that nice ionic bond because fluorine is going to take potassium's electron. Excellent. All right, so a covalent bond is something that we've already talked about. Remember, it's that sharing, right? They're holding hands. Those two elements are holding hands. You didn't just dump off your electron and be like, I'll come back and get it later. No, you're holding hands. You're sharing your electrons. So you're like, I'm happy, you're happy, we're totally stable. That is a covalent bond. That is the strongest of all the bonds. Really, really strong bond, super hard to break. Now, when we're talking about any kind of bond, including ionic bond, it takes energy to form a bond. So imagine that these atoms kind of had to gather the energy to form that bond. This is also true when they break a bond. So when you make a bond, you kind of store energy in this bond. When you break said bond, you've now released that energy back out into the system. Okay, so if your body is trying to go through a chemical reaction, it takes energy. It requires energy to go through a chemical reaction, right? You have these two atoms just kind of floating around, you want to stick them together, it requires energy. Okay, now this is known as potential energy because the energy is stored in this bond, which means it has the potential to be released. Okay, as soon as we break the bond, we're now releasing said potential energy. So now it is available to use. Okay, so you make the bond, you store the energy, you break the bond, you release the energy. Okay, that's true of all these different bonds that we're going to be learning about. Okay, so here's some classic examples of covalent bonds. Now, anytime you see a solid line written just like this, or like this, or like this, these are all covalent bonds. When you see a dotted line, we're going to talk about those later, but those are known as hydrogen bonds. So anytime you see a solid line like these, you can know, oh, okay, that's for sure just a covalent bond. Now, we can have single covalent bonds, like here, and this case would be like we have two hydrogen molecules, and they're sharing their electrons. So they each have one electron, and they're sharing it. So now they each have two. So they're very happy. So when you see each of these lines, you can almost imagine like drawing a little dot on either side, right? A dot right there and a dot right there, and they're connected. That means in this one line, there are two electrons. Okay, so every line, there's two electrons. In this case, we form a double bond. Okay, so oxygen has 6, oxygen has 6. But it's like, hey, if we share 2 of our electrons with each other, then we'll both have 8. You'll have 8 and I'll have 8, and we'll both be happy. And this is how we get atmospheric oxygen, right? It's O2. It's O2 because they form these little double bonds right here. So in this case, it's 1, 2, 3, 4 electrons are being shared right here, okay, in those two little lines. Here's our good friend methane again, right? We have the carbon surrounded by, right? So, and again, we can kind of count the number of electrons in these bonds. So hydrogen needs 2. It has 1, 2. Perfect. This hydrogen needs 2, 1, 2. This hydrogen needs 2, 1, 2. This hydrogen needs 2, 1, 2. Each of those 4 hydrogen molecules are super happy. Okay, and that's exactly what you can see right here in this picture. Now the carbon needs 8. 1, 2, 3, 4, 5, 6, 7, 8. Carbon's happy. This is why methane is, again, kind of a problem actually in our environment, because methane, even though it's really nasty and kind of toxic, it's super stable and therefore hard to break down. So thank you, cow, and cows in your butts. Which actually is kind of an ecological problem that scientists are trying to work on, because cows are so important for things like food. Right? We've been breeding them a lot, and we keep them at a lot higher numbers than they historically were. And so now cow farts are kind of, you know, adding to the whole climate change kind of thing, which is really weird that literally just the gas coming out of a single animal can change our entire ecosystems. Crazy, but true. And we're going to learn all about that later on in the semester. All right, our last type of bond, we learned about ionic bonds, we learned about covalent bonds. We're learning about hydrogen bonds now. Now, hydrogen bonds are a type of covalent bond, but they're the weakest of all the bonds. Okay, so covalent bonds are the strongest of all the bonds. Hydrogen bonds are the weakest of all the bonds. And that's because hydrogen is just one little molecule with one little electron that it's trying to share. So that bond can actually be chopped off kind of easily. So this is where we're going to be getting to talk about water, and this is going to be the second part of our Chapter 2 lecture. So I'm going to go ahead and pause right here before we actually get into hydrogen bonds. And we're going to come pick this up with part 2 of chemistry.